Welcome to Theory of Computation. This is lecture number 7. In the last lecture, we discussed the Church-Turing thesis that says that the intuitive notion of algorithms is the same as the formal mathematical concept of Turing machines. This allows us to ask many problems formally and precisely. For example, we looked at Hilbert's 10th problem, and we realized that we can pose Hilbert's 10th problem as a language. Hilbert's 10th problem can be posed as the following language. The language consists of all encodings of multivariate polynomials which have integral roots. We then stated Matisevic's theorem, which says that Hilbert's 10th problem is undecidable. What it means precisely is that there is no Turing machine that would halt on all inputs and decide if a multivariate polynomial has integral roots or not. Today's lecture is going to be mostly on decidability. Today we would look at examples of many languages that are decidable. A language is decidable if we have a Turing machine that accepts that language and halts on all inputs. Or intuitively, a computational problem is decidable if we can find an algorithm that solves that problem. The outline of today's lecture is as follows. First, we would look at what decidable languages are. After that, we will study some decidable problems concerning regular languages. Then we would look at some decidable problems concerning context-free languages. After that, we will discuss the acceptance problem for Turing machines and the halting problem. And in the end, we will comment on the undecidability of the halting problem. Let's get started. Recall that we always consider our problems as languages. All our problems are subsets of 0, 1 star, which is our favorite alphabet. Now, what we want to do is, given a language, construct a Turing machine that accepts that language and halts on all inputs. More precisely, we want to find a mechanical procedure that would tell us whether a given string is in the language or not. And when we say that the Turing machine must halt on all inputs, we want this procedure to be a finite procedure. The Turing machine, after a finite number of steps, must give us an answer. Yes, the string is in the language, or no, the string is not in the language. Let's go back and recall the precise definition of what a decidable language is. Remember that a language is a subset of sigma star. A language is called decidable if there exists a Turing machine M that halts on all inputs and the language of that Turing machine is A. So A is decidable if I can find a Turing machine whose language is A and the Turing machine halts on all inputs. In other words, if X is in A and I run the Turing machine on input X, M must accept this input, and if X is not in A, then M must reject this input. Intuitively, M is just an algorithm that solves the yes-no problem A. So, that is the precise definition of what a decidable language is. So, what kind of languages are decidable? That's a very interesting question. Of course, there are many languages that are decidable. In fact, there are infinitely many languages that are decidable. But we would like to study now what kind of questions we can answer mechanically. You must remember that you must have studied deterministic finite automata in your previous courses. A DFA is a very simple model of computation. Recall that a DFA has just a set of states. It has only a read-only tape. What it does is, in one single step, it looks at the current symbol from the input and the state that is in. And by looking at these two things, it decides to change its state to another state. However, the tape head is only moving in one direction and it always shifts to the right. When the DFA finishes reading its input, if the DFA reaches an accept state, the input is accepted. If it reaches a reject state, the input is rejected. The languages accepted by DFAs are precisely regular languages. You must have studied that in your previous courses. In this course, we will not be studying regular languages in the regular sense. We would not be designing DFAs and so on and so forth. However, we'll be asking another different question. What we will be asking is, what questions about DFAs can be answered using Turing machines? In other words, we will be asking about problems concerning regular languages which are decidable. Let's start with a simple problem. Let us look at this language, which is what we call a DFA. It consists of a set of all strings which are encodings of a DFA followed by a string such that the DFA accepts the given string. Let's be more precise and let's look at this definition. A DFA is the encoding of all pairs B, W, where B has to be a DFA and W has to be a string, and the DFA B must accept the string W. So, in order to understand what this language is, let us look at a few examples of the kind of strings that are in this language. You remember from the last lecture that we said that almost any mathematical object can be encoded as a string. So you can take a DFA, you can write down its transition table and then encode it as a 0-1 string. So this language will consist of all encodings which encode a DFA and a string, and the string must be accepted by the DFA. There is a very simple way of thinking about this language. You can ask yourself that somebody will give you a DFA and a string, and they'll ask you whether the DFA accepts the given string. However, you are not supposed to answer this question yourself. You're supposed to devise an algorithm which will do this for you. So you're supposed to give a description of a Turing machine which will accept this language. Let's be clear and look at an example of the kind of things that are in this language. Let's look at a picture of two DFAs that's given on the slide. The first DFA has two states and the second DFA has two states. And as you can see, both these DFAs are extremely simple. So in this case, as you can see, the DFA B1 will accept the string 1. So the encoding of B1, 1 is in a DFA. However, the DFA B1 will not accept the string 0, 0, 0. So the encoding of B1, 0, 0, 0 is not in a DFA. Similarly, the DFA B2 will not accept the string 1. So the encoding of B2, 1 is not in a DFA. And lastly, since the DFA B2 does accept the string 0, 0, 0, therefore the encoding of B2, 0, 0, 0 is in a DFA. What we want to show is that this a DFA is decidable. Well, how do we show that a language is decidable? For that, we will have to give a Turing machine that accepts precisely the strings that are in the language and rejects all the strings that are not in the language. The question that we want to ask is a DFA decidable? Let's ponder on this question for a bit. We are asking if we can make an algorithm, a Turing machine, that will take as an input a description of a DFA B and a string W in 0, 1 star and tell us if B accepts W. So what we are asking is, can an algorithm decide if a DFA accepts a given string? Can we have a mechanical procedure which can take a description of a DFA and a string and tell us whether that DFA will accept that string or not? Well, is this language decidable? This language is decidable, and we would see why. We can devise a Turing machine, since a Turing machine can simulate the behavior of DFA. Here is a high-level description of such a Turing machine. On input, which is an encoding of a DFA B and W, the Turing machine will simulate the behavior of B on the string W. If B reaches an accepting state, then we will accept. If B does not reach an accepting state, we will reject. As you can see, the description of this Turing machine is a high-level description. We can try to give an implementation level description of this Turing machine. The question that arises is, how can a Turing machine simulate the behavior of a DFA? Once we have the implementation description, it will become clear to you that you can convert this description into a formal Turing machine. Let's look at the implementation description. Suppose we have an input which is b, w, where b is a description of a DFA and w is a string. What we can do, first of all, we will have a Turing machine which uses lots of tapes. So we will use 3 tapes in order to solve this problem. First, what we'll do is we'll copy the transition function of b onto the second tape of the Turing machine. Then we will write down the current state on the third tape of the Turing machine. Then we will take the first tape of the Turing machine and write w on it. Now we will run a loop which will run for I going from 1 to the length of the string steps. And each time we go through this loop, we will simulate a single step of the DFA. This is done by scanning the heads, consulting the transition function on the second tape and the current state on the third tape. By doing this, we'll be able to simulate one step of the DFA. After that, we run this loop for as many times as there's the length of the input. At the end, we will have the final state to see if this final state is one of the accepting state. If it is, we will accept, otherwise we will reject. The description of this Turing machine tells us that this language is decidable. It is possible for a Turing machine to tell whether a DFA accepts a given string or not. It does not require any extraordinary intelligence. There is a simple mechanical procedure that can take a DFA and a string and tell us whether that DFA will accept this string. All we have to do is simulate the behavior of the DFA one step at a time. It is very critical to note here that a DFA accepts a string in, so suppose you give a DFA a string of length n, then the DFA will accept the string in n steps, or it will not accept the string in n steps. So therefore, the process that we have described is finite. In other words, the description of our Turing machine describes a decider. It halts on all inputs and it gives us the correct answer. Namely, it tells us whether a string is accepted by a DFA or not. Let's look at another question. You must have also studied non-deterministic finite automata in your previous courses. So, what about a similar question about non-deterministic finite automata? Let's look at the question more formally. Let ANFA be the description of b, w, where b is an NFA now. So ANFA is the encoding of pairs b, w, where b is a non-deterministic finite automata and w is a string which is accepted by this non-deterministic finite automata. Is ANFA decidable? Once again, let's think about this problem intuitively. What is the input that is given to you? You'll be given a description of a NFA now, a non-deterministic finite automata, followed by a string. And you have to tell whether this non-deterministic finite automata will accept this string w or not. So you have to design a Turing machine which will take a description of a non-deterministic finite automata and a string, and it would tell us whether the NFA accepts the given string. Of course, we can approach this problem as we did before, using simulations. What we will have to do is to convince ourselves that a Turing machine can simulate an NFA. That's not going to be so difficult, because as you know, a NFA, instead of being in a single state, is in a set of states. So we can essentially use the same idea as we did before, except for now we will have to keep the track of set of states that the NFA is in currently. So we can use simulations to show that a NFA is also a decidable language. However, there is another way to show that this language is decidable. You have studied that every NFA can be converted into an equivalent DFA. You must have studied that in your previous automata course. You also know that given a DFA, there is a mechanical procedure, there is an algorithm that converts the NFA into a DFA. So what we can do is use that algorithm to design our Turing machine. Suppose you're given an NFA and a string and you want to know if this string is accepted by the NFA. What you can do is take the NFA and convert into a DFA first. Now all you want to know if this particular string is going to be accepted by this DFA or not. But that's a problem we have already solved. So we can invoke our previous Turing machine as a subroutine and solve this question. Let's look at the description of this Turing machine more precisely. Suppose you have the input b, w, where b now is an NFA and w is a string. We will convert b to an equivalent DFA C. Now we will run our previous machine, the machine that we designed for testing if a string is in a DFA, on this input, on the input c, w. If that Turing machine accepts, we will accept this input, otherwise we will reject. So as you can see, one particular language can have many deciders. There can be many ways to solve a particular problem. And a language is decidable if there is at least one way, at least one Turing machine that decides that problem. So a decidable problem is one for which you can find at least one algorithm. Let's look at another problem now. This problem concerns regular expressions. Suppose that I give you a regular expression and a string, and I can ask the question if the string is generated by this regular expression. Does this regular expression generate this particular string? We can pose this question once again as a language. That's what we call AREX, standing for strings accepted by regular expressions. Probably GREX would have been a better name because strings are usually generated by regular expressions, but nevertheless, we will stick with our previous notation. So AREX is the set of all encodings of R, W, where R is a regular expression that generates the string W. So for example, the pair 0 star 1 star followed by 0011 is in ARX because 0011 is generated by this particular regular expression. On the other hand, 0 star 1 star comma 10011 is not in ARX because this string is not generated by the regular expression. Another string which is in AREX is the encoding of 10 or 1 star followed by the string 10. Since this string is generated by this regular expression, therefore this encoding would be in AREX. Lastly, 10 or 1 star, comma 0011 is not in AREX because this regular expression only generates strings that are starting with a 1 and this particular string does not start with a 1. So, is this language decidable? Is it possible for us to give a regular expression followed by a string to a Turing machine, and that Turing machine will tell us whether this string is generated by that regular expression? Once again, we can start thinking about this problem intuitively. If I have a regular expression and a string and I'm asked the question, is this string generated by this regular expression, how would I approach the problem? Once you learn how to approach the problem yourself, then you can formalize your approach into an algorithm which eventually becomes a decider. Well, one way to approach this problem is to take the regular expression that I have and start writing down the strings that it generates. I can start looking at the kinds of strings that it generates. and I can see if the string in question is one of them. However, this approach is not very promising because, as we know, regular expressions can generate infinite number of strings. So this seems to be a very long search. On the other hand, we can approach this problem in a very different way. In your automata courses, you have studied that DFAs exactly accept regular languages. So for every DFA, you can construct a regular expression which will generate all the strings that are accepted by the DFA. Similarly, given any regular expression, you can construct a DFA which accepts exactly those strings that are generated by this regular expression. Not only that, but you also studied algorithms. Given a regular expressions, you studied algorithms, methods for converting these regular expressions into DFAs. Well, in this case, we can solve the problem using this idea. What we do is we take the regular expression and we use one of the algorithms that we studied in our basic automata courses and convert this regular expression into a DFA. Now what we have done is reduce the problem to an already solved one. All we have to do is now ask if this string W is accepted by this DFA or not. Let's look at the solution in more detail. Suppose the input is R, W, where R is a regular expression and W is a string. The first thing this Turing machine will do is convert the regular expression R into equivalent DFA C. Now it will run our previous Turing machine to find out if W is accepted by C. If M of D accepts, which means it declares that W is accepted by C, this Turing machine will accept. Otherwise, it will reject. So you see, what we have done is converted the problem of telling if a string is generated by a regular expression into the problem of telling whether a string is accepted by a DFA. So all these problems are decidable. Of course, what we have been doing is giving very high-level descriptions of these Turing machines which decide these problems, these languages. However, all these descriptions which are high-level can be converted into implementation-level descriptions first, and then formally to formal Turing machine descriptions, formal descriptions of Turing machines. Therefore, all these problems are decidable. Let's now look at an even more interesting question. This problem is called eDFA. This is the set of all encodings of DFA whose language is empty. So, you will be given a DFA, a description of a DFA, and the question that you have to ask is if this DFA accepts the empty language, or in other words, if this DFA does not accept any string at all. How can we solve this problem? Once again, we can think of a possible approach. One approach would be that we go through all the strings and one by one simulate them on our DFA. If our DFA accepts any of these strings, then the language of this DFA is not empty, and so we can reject the input. On the other hand, if the DFA does not accept any of those strings, well, there are infinitely many of those strings, so our computation will go on forever. So this approach does not lead us to the design of a decider, because a decider is supposed to halt on all inputs and give the answer in finite amount of time. So we have to think of a clever way of solving this problem. So given a DFA, you want to know if it does not accept any strings. The problem is that there are infinitely many potential inputs to the DFA, and therefore we cannot use simulations directly. Can we solve this problem in a clever way? What we want to do is get rid of this infinite number of checks that we have to do and somehow use a clever method so that by analyzing the description of the DFA, we can tell whether its language is empty or not. Here is a very nice way to solve this problem. Let's look at this Turing machine that decides this language or this algorithm. The emptiness problem for DFAs seems to demand that we tell whether the DFA does not accept any of the potential infinitely many inputs to it. So we may start suspecting that this is perhaps a difficult question, and designing a TM that tells us in finite time if the language is empty may not be possible. However, a little thought shows that it is possible to find a TM that decides this problem. The idea is that if we want to tell if a language of a DFA is non-empty, all we are trying to see is if it is possible to reach some accepting state through some input. So we can use the following simple method. Suppose the input is the description of a DFA A. What we are going to do is mark the start state of this DFA. And now we will repeat this n times, where n is the number of states in this DFA. We will mark any state that has a transition coming into it from any state that is already marked. We continue this process for n times, and after this, if any accept state gets marked, we reject the input, otherwise we accept the input. The description of the algorithm that I have given you is very simple. See, the start state of the DFA is reachable. Therefore, I mark it. Now, all the arrows that are coming out of the start state, I mark them in the next step. And then all the arrows that are coming out of there, I keep marking them. This way I keep marking, and after a while I will not be able to mark any more states. All the states that got marked are the ones that are reachable from the start state. So those are the states for which I can give an input and make the DFA reach those states. Now, if any accepting state is reachable, that means the DFA accepts at least one string. But if no accepting states are reachable, that means the DFA does not accept any strings. So if any accepting state ever gets marked, I know that the DFA accepts at least one string, and therefore I reject that DFA. On the other hand, if no accepting states get marked, then no accepting states are ever reached on any input, and therefore I know that the language accepted by this DFA is empty, and therefore I can accept this state. You can easily convince yourself that if after n steps one of the states doesn't get marked, then no matter how long you run this algorithm, it will never get marked. In fact, you must have studied the reachability problem in your algorithms courses. Here is a more familiar way to solve this problem. This method can be explained simply as follows. On the input, which is an encoding of a DFA, what we do is we perform a depth first search or a breadth first search on the transition diagram of A starting from the start state. If the final state gets marked, we reject the input, otherwise we accept. Notice that we have managed to avoid a potential infinite computation by a clever method. So this tells us that if a problem looks difficult, we must think again. We must think of ways to avoid potential infinite computations. That's really what is at the heart of decidability. Designing algorithms which don't compute forever. In fact, something that computes forever is not even an algorithm, it's not a decider. But problems which look as though a naive approach will require infinite amount of computation to solve them, we can come up with clever ways and avoid those potential infinite computations. So, whenever you are asked to show that a language is decidable, you must think of coming up with an algorithm that will eventually stop on all inputs. It will not go into an infinite computation. Let's look at another problem which has a similar flavor. This is called the equivalence problem for DFAs. In this language, you're given two DFAs, and the question that is being asked is if both these DFAs accept exactly the same language. So let us look at this problem a bit more formally. EQ DFA is the set of all encodings of pairs of DFAs, A and B, such that the language of A is equal to the language of B. The input to this problem is the description of two deterministic finite automata A and B. We have to decide if the language of A is equal to language of B. That is, if they accept exactly the same language. Note the problem on the surface again looks very difficult. We have to make sure that A and B exactly accept and reject the same strings. They accept the same strings and they reject the same string. However, the number of potential strings to be tested is infinite. So it would be futile to simulate A and B on all possible strings. The process will never end. This problem looks more difficult than the one that we have seen before. This problem, the input is two DFAs and we have to tell whether they accept exactly the same language. How can we do that? Well, one naive approach that was outlined for you 2 minutes ago is to run both these DFAs on all possible strings. But that approach is not fruitful because there are infinitely many strings on which you will have to test these DFAs. Can we come up with a clever way to avoid this potential infinite computation? Can we actually look at these two DFAs, analyze them more cleverly, and be able to tell whether they accept exactly the same languages or not? Fortunately, there's a way to do so. Let's look at it. So we may start by suspecting that this is perhaps a difficult question, but that's not quite true. Suppose that the language of A is not equal to the language of B. Then we notice that there is either a string X in the language of A intersect the language of B complement, or there's a string X which is in the language of B intersect language of A complement. This is very simple. If two sets are not equal, then you can find an element which is in one set but not the other, or you can find an element which is in the second set but not the first. That's the only way two sets can be unequal, is if you find one element on which they differ. Alright, so what can we do? Well, we can say that these two languages are going to be different if and only if this symmetric difference is non-empty. Let's look at what the symmetric difference is. The symmetric difference is L of A intersect L complement of B union L of B intersect L complement of A. Now, if this symmetric difference is empty, then these two languages must be equal. This is shown to you by the following Venn diagram. As you can see in the Venn diagram, if two sets are not equal, then you can find at least one element in the symmetric difference. Now our plan is as follows. What we will do is we will take our DFA A, we will take our DFA B, and we will construct a new DFA C which accepts the symmetric difference of these two DFAs, or more precisely, whose language is the symmetric difference of the languages of these two DFAs. Once we have done that, then our task would be to find out if C accepts the empty language. Well, if C accepts the empty language, then L of A must be equal to L of B. On the other hand, if C does not accept the empty language, then there is at least one string which is in A language of A but not in the language of B, or there is one string which is in the language of B and not in the language of A, and therefore these two DFAs accept different languages. We know the following properties of regular languages. If P is regular and Q is regular, then their union is regular. Furthermore, we know that given two DFAs D1 and D2, we can construct a DFA D such that the language of D is the union of these two languages. Of course, you have studied such algorithms in your automata class. You have learned how to take a DFA D1 and how to take another DFA D2 and construct a new DFA which accepts the language which is the union of the languages of these two DFAs. And there's a very simple algorithm to construct this DFA D. This is one fact that we will use from properties of DFAs that we have already studied. Another fact we will use is the following. If P is regular, then the complement of P is also regular. Furthermore, if you are given a DFA D1, we can construct a DFA D prime such that the language of D prime is the complement of the language of D. This is very easy to do. You must have already seen this algorithm that converts a DFA into one that accepts the complement of the original. Well, all you have to do is change all the accept states to reject states and all the reject states to accept states. So this is also a very simple procedure. So we have algorithms which take two DFAs and output a DFA that accepts the union of the languages of the two DFAs, and we have an algorithm to which we can give a DFA and it will give us a new DFA that accepts the complement of the original DFA's language. So putting these two things together, what we can do is the following. We can make a DFA C such that the language of C is the symmetric difference of the language of A and the language of B. As you can see, the only operations required to compute the symmetric difference are unions, complements, and intersections. And we know how to do all of these. So we have the following description for a Turing machine that decides this equivalence problem. On input, which is encoding of A and B, where A and B are DFAs, we will construct the DFA C as described above. Now, if the language of C is empty, we will accept, otherwise we will reject. So, how will we find out if the language of C is empty? Well, C is just a DFA, and we have already solved the emptiness problem for DFAs. So, we can use our previous Turing machine as a subroutine here, our previous algorithm as a subroutine to solve the emptiness problem of C. So what we have done is converted the equivalence problem into the emptiness problem. Given two DFAs A and B, what I do is I construct C and solve the emptiness problem. And the emptiness problem tells me whether the language of A was equal to the language of B. Well, these were all very interesting questions about regular languages. But in your automata courses after studying regular languages, you must have studied context-free grammars. So what can we say about similar questions about context-free grammars? Can we solve these problems using Turing machines? Or the related problems about context-free grammars also decidable? Is there a Turing machine that can tell us many interesting things about context-free grammars? Well, let's have a look at the first problem. This problem called ACFG consists of a grammar and a string G, W, where G is a context-free grammar and W is a string, and the grammar G must generate the string W. So, is this language decidable? Is it possible for me to make a Turing machine which will analyze a context-free grammar and tell me whether the context-free grammar will generate a given string? Well, how would we approach this problem? Once again, what we can do is we can take our context-free grammar and start generating strings from it. And we can hope that we will encounter the string W. But once again, this is not a very good approach because a context-free grammar can generate potentially infinitely many strings, and there seems to be no way of us telling whether W will eventually be generated or not. Can we approach this problem in a different way? Can we solve this problem in a way so that we can avoid this infinite computation? This would tell us that this problem is decidable. Well, luckily, you had studied that every context-free grammar can be converted into a very special form, which is called Chomsky's normal form. Once a grammar is converted into Chomsky normal form, then it has a very, very important property. If you have a string of length n then I can generate that string of length n from the grammar in 2n minus 1 steps. Well, so this means I will not have to generate infinitely many strings to find out whether a given string is generated by a grammar or not, provided that grammar was in Chomsky normal form. Another nice thing that you learned in your automata courses was an algorithm that takes any grammar and converts it into Chomsky normal form. That means that you can use that algorithm in order to show that this language is decidable. Let's look at the description of the Turing machine that decides this language. The input to this problem consists of two parts. The first part is going to be a context-free grammar G, and the second part is going to be a string W. We have to decide if the grammar G generates W. And we want to show whether this language ACFG is decidable. So on input G, W, we will convert the grammar G into Chomsky normal form to get a new grammar G prime. Now, the grammar G prime is in Chomsky normal form, and we'll list all its derivation, which consists of 2n minus 1 steps. Recall that we are going to have only finitely many derivations, which consists of 2n minus 1 steps. Here, n is the length of the string W. Now, if we will check if one of these derivations generated W, if it did, we will accept, otherwise we will reject. So, here, in order to show that this language is decidable, we're using our knowledge about context-free grammars. We're using very specialized knowledge. One, we're using the fact that every grammar can be converted into Chomsky normal form, and we have an algorithm for doing that. Second is, we're using the fact that if a grammar is in Chomsky normal form, then it generates a string of length n in at most 2n minus 1 steps. Therefore, we only need to check derivations of length 2n minus 1 to see if the string that we are interested in ever appears or not. Once again, by using specialized knowledge about context-free grammars, we've been able to avoid infinite computation. We have been able to show that given a context-free grammar, we can tell whether it generates a string or not in finite amount of time using a Turing machine. Therefore, this language is decidable. So the acceptance question for context-free grammars is decidable. Let's look at another problem which is more interesting. ECFG consists of encodings of all context-free grammars whose language is empty. Note once again that the problem on surface looks very difficult. We have to make sure that G does not generate any strings. In other words, we would like to show that starting from the start symbol of this grammar, we can never get to a string which consists only of terminals through a derivation. Since there are potentially infinitely many derivations, the problem looks difficult. So the naive approach to this problem is, once you're given a context-free grammar, you can try all possible derivations and hope that at least one string over the terminals is generated. If one string over the terminals is generated, then you would know that the language of this grammar is not empty. On the other hand, this approach will not work if the language of this grammar is empty, because there are infinitely many potential derivations. So we need a more sophisticated approach in order to show that this problem is decidable. Fortunately, we do have one sophisticated approach. Let's have a look at it. The idea is that we want to tell if the language of CFG is non-empty. All we are trying to see is if it is possible to generate all terminals starting from the start symbol. So we can use the following simple method. Suppose the input is an encoding of a context-free grammar. We can mark all the terminal symbols. Now, what we do is, if we find a production which is U goes to U1, U2, U3 all the way up to UK, and in this production all the things on the right hand side are already marked, then we will also mark U. We will continue doing this till no further non-terminals can be marked. If at the end of this algorithm the start symbol gets marked, we will reject the input, otherwise we will accept the input. What we're trying to do here is mark all non-terminals from which we can derive a string of terminals only. Therefore, if we have a non-terminal that only goes to terminal, it will be marked in the first phase. On the other hand, if there's a non-terminal that goes to a non-terminal which only goes to terminals, that would be marked in the second phase, and so on. If at the end of this process the start symbol gets marked, then we know that we can derive at least one string from the start symbol, and therefore the language of this grammar is not empty. On the other hand, if the start symbol does not get marked, we will know that the start symbol can never derive a string of terminals, and therefore the language of this grammar is empty. So the emptiness problem for context-free grammars is also decidable. Let's look at one more question. This is called the equivalence problem for context-free grammars. So the equivalence problem for the context-free grammars EQCFG is you're given two context-free grammars G1 and G2, and the question is whether the language of G1 is equal to the language of G2. Formally, it's the set of all pairs G1 and G2, where encodings of all pairs G1 and G2, where L of G1 is equal to L of G2. Note that once again this problem looks difficult. It looks like we have to check if all the strings that are generated by G1 are also generated by G2 and vice versa, and the number of potential strings is infinite. So a naive approach will not work, because that would take infinite amount of time, whereas we want to show that this language is decidable. The question now is, given two context-free grammars, can we come up with an algorithm which will tell us whether these context-free grammars generate the same language or not? In all the previous cases, we looked at various problems, and we saw that problems on the surface looked like they required infinite amount of computations, but we were able to find clever ways of solving those problems and actually finding deciders for them, finding algorithms for them. Well, this problem is very different. The equivalence problem for context-free grammar is undecidable. There is no Turing machine that accepts this language. There is no algorithm that can take two context-free grammars and tell you whether they accept exactly the same language. In today's lecture, we will not prove that the equivalence problem for context-free grammars is undecidable. We will do that later on in the course. However, this problem is extremely interesting. It's amazing that we can actually prove that this problem cannot be solved by an algorithm. The first undecidable problem that we will study is not going to be the equivalence problem for context-free grammars. In fact, it's going to be a different problem. So far, we have been looking at problems concerning regular languages or DFAs and context-free grammars. Now we will look at the acceptance problem for Turing machines. The acceptance problem for Turing machines is defined as follows. You are given a Turing machine M and a string W, and you have to tell whether this Turing machine will accept this string W or not. So formally, the acceptance problem is defined as follows. ATM is going to be the set of all encodings of M, W, where M now is a Turing machine and W is a string that is accepted by this Turing machine. This is the acceptance problem for Turing machines. In the next lecture, we will look at this problem, and we would also look at the so-called halting problem for Turing machines. We will show that both of these problems are undecidable. which means that there is no algorithm or there is no Turing machine that accepts these languages. There is no algorithm that can solve these problems. Those two problems are going to be our fundamental undecidable questions. We will use those to show that several other problems are undecidable, and that would also include the equivalence problem for context-free grammars. I will see you in the next lecture. Thank you and goodbye.